Hi everyone, my name is Srishti Bhatt and I'm a data science graduate student. I hope everyone's doing well under these trying times. So I'm here to present my Capstone project, which is an automated modeling pipeline. It is basically an end-to-end automated system for generating predictive models using raw data. So these are the contents that we're going to go through in the presentation today. So beginning with why feature engineering is important in the data science domain. We need to prepare the proper input data set which is compatible with the machine learning algorithm requirements. So modifying, deleting, and combining features results in a new set that is more adept at training a model. Feature engineering is a vital part for data preparation. The output from the feature engineering is fed to the predictive models and the results are then cross-validated. So this significantly improves the performance of the machine learning models. As you can see from the figure here, for building a successful model, feature engineering is the most important parameter amongst others such as data cleaning, model training, etc. Next, I would like to go through the purpose of automation of feature engineering. So out of all the core steps, this is the task which takes up most of the time by data scientists. And if it is done correctly, it can increase the power of the predictive power of the machine learning algorithms that we are by creating new features from the raw data, which will help facilitate the machine learning process. So in short, it will save us time. It will build better predictive models and create meaningful features and reduce the data leakage that happens. So when applied to a data set, automated feature engineering can reduce the machine learning development time by almost 10 times as compared to manual feature engineering, while bettering the performance of the model. It also reduces the resource allocated to the project. So the background of my project, as I've mentioned before, is to benefit the model performance and accuracy and reduce the resource allocation. The objective was to automate this task, and the scope was to extract, that means creation of new features, and then selecting amongst the large range of features. So the data set that I've used for this is the home credit default data set. Home Credit uses this data to predict their clients' repayment abilities. The target variable, the predictor here, is binary, indicating that 0 indicates that the client will be able to repay the loan, whereas 1 indicating that the client has difficulties repaying the loan. This data set has around 58 million rows spread across 7 tables. So this meant that consolidating all the information about each client in one table. My first attempt at the problem was to create a baseline model using manual feature engineering. And the second was this figure here shows us the schema of the data set used. So the second algorithm that I used was the deep feature synthesis, which is an algorithm that automatically creates features between sets of relational data. So for this, I've used an open source Python package, which is called Feature Tools, that applies this deep feature synthesis to a user-defined entity. So each table here is an entity, and the relationship, for example, one to many, and then parent-child relationship. Altogether, the table and the relationship constitute the entity set. So this package has a few functions which are called primitives, which are applied to the existing features to generate the new ones. There are primarily 2 types of primitives. So we can understand this from the example below. Okay, so for example, here we have 2 tables. The members is the parent table and the transactions is the child entity. So once we apply aggregate primitive, for example, we're applying sum here to the amount paid. So this shall sum up all the amounts paid, and the features would roll up to the parent level. The transformation primitives are applied to either the parent or the children entities, and they are applied on a single row. So the output data frame that we get here has the same number of rows as the parent. entity. So the framework includes feature extraction using deep feature synthesis algorithm, which will generate a CSV file which will contain all the newly created features. This then is the input to another feature selection pipeline in an automated feature engineering pipeline, and which takes the CSV file as the input. And the third task was manual feature engineering. So the feature selection is the process of selecting variables which contribute to the predictor variable or the output. Having any number of irrelevant features would just reduce the accuracy of the model and increase the training time. So in order to avoid that and avoid the curse of dimensionality, we have certain criteria for the data preparation, which would include dropping the duplicate columns, dropping columns with high proportion of null values. If two columns are highly correlated, we would drop one of them. And if a certain column has all the same values for all the rows, we would drop that column. So the characteristics of feature selection pipeline had a class which has a fit and transform method. So the fit method would find the list of columns to drop and keep, and transform would return the resultant data frame, and fit transform would combine them. Components of feature selection pipeline can be arranged in any desired order, and I also made use of the built-in plotting capability to plot the importance of the features. So this makes it clearer. This gives a clearer picture of the pipeline that I've used. There are certain threshold values that I've used. For example, if a column has 70% of the values in the column are missing, then I would drop them. I would drop the duplicate columns. And for highly correlated, that means if two columns are 90% same, I would drop them. And I also used a random forest selector. So this would select the features with 80% overall importance. This is a snippet of the functions being called. So for the data set, when this pipeline was applied to the data set, the home credit data set, initially there were around 210 features. And after the feature extraction class, we had around 1071 features, and these are the results. So 303 columns were dropped due to missing values, 42 columns dropped due to duplicate values, and so on. So ultimately, out of 1071 features, we selected only 580. So the model used here was the gradient boosting model. It is a tree-based algorithm which trains the model in a gradual, sequential, and additive manner. The parameters passed here were num boost rounds, which is the number of training rounds or the boosting iterations that we need, which is around 10,000. Early stopping rounds indicate that the model will keep on training until the validation score stops improving. And the n fold is 5 here, which indicates that the original data set will be randomly partitioned into 5 equal size subsamples. So the results also included a model comparison. So the baseline model, which was created using the conventional method, used only basic transformation variables like sum and aggregation functions, whereas our model, which was derived by using feature extraction class, used around 19 aggregation and transformation functions. Initially, the number of features were 30, and after one hot encoding, they were around 210. So, whereas for the automated model, the around 580 features were used. We also see that there is a significant increase in the cross-validation AUC, and the time taken, the development time was also significantly reduced. For the manual feature engineering, it is a tedious and an error-prone, time-consuming task. So, and it is problem dependent, and we have to rewrite it for all the data set, whereas the automated one can be used for other data science problems. the number of estimators trained were 142 for the gradient boosting model. Feature tools, this algorithm has the ability to stack primitives on each other, which will generate more complex features. We can control the complexity of the features based on the maximum depth that we provide for this. So the baseline, the manual feature engineering, the baseline model that we created, the most important feature for that was loan rate, and the model that we created has a variable which has a depth of 2. So there are certain limitation challenges for this. Deep feature synthesis runs with pandas, which has, therefore there is a limitation on the size of data that we can use. The one that I used was almost 2.5 GB, and hence this is something that needs to be taken into consideration. And this pipeline does not replace a data scientist. There is manual intervention is still required, and new features which are generated may be hard to interpret in a business context because the features used here are complex. Thank you.
Great, thank you. Good timing, it's right on time as well. Okay, so we certainly have time for a certain question or two.
Yeah. Sure, Steve. And I think this is a very interesting and important project. You did a good job. I have a question. The first tool which you mentioned is called DFS.
Yes.
Yes. Okay. Now there is an example which will show how it works, right? Can you show that slide, please?
For this one.
Yeah, right here. Okay, thank you. Okay. Now here, so the example basically shows that for different transactions, you take the amount paid and then add them all together.
Yes.
For the same user.
The parent.
Yeah, is a member, right?
Sorry.
The parent is member, right?
Yes. So this table shall have information for each client, and
right.
Each client might have numerous amount paid. So it will sum up and it will give it for each client, give results for each client.
Right. So what I'm trying to ask here is, okay, so basically looks like you're going to match the user ID, right? And then
yes,
basically to identify this transaction related to this member, right?
Yes,
and
that's correct.
Amount paid will be adding up together. Now the question is, how is this rule to add actually to sum them all together? Is this a rule which you gave to the DFS as input? Is that right?
Right. So we can implement DFS through this feature tools library, Python library, and this library contains primitives. Those primitives are functions which we have to provide. We just have to provide the primitives, and we have to describe the entities and the relationship between them, and it shall just give the output.
Right. So I think my question following here is, because you have to actually find out the rule, which is by human, right? So the human has to define the rule. How to merge in the feature together?
In the library, we do not have to define it.
No, I think because see the arrow above the DFS, right?
Yes.
This aggregate primitive sum, right? But I mean, some apply to which feature, and this has to be decided by. Is that decided by the user, right?
No, that is not decided by the user. We just have to define the entities and the relationship between the entities, and it has some predefined functions which are called primitives, and they will return the various aggregations and transformations.
Yeah, I understand the sum function is defined by the system, but what I'm saying is the sum is applying to which feature is defined by the user, right?
No, that is not. It generates thousands of features on its own. It will use different columns to generate these features.
But how does DFS know it should sum the amount paid and instead of sum the transaction data?
So that library is already automated. So these functions are applied to n number of columns. It will determine the type of the data type of the column, and it will apply different primitives on all of them. That is the reason why we get a very large number of features from as a result of this pipeline.
Okay. Okay, I'll stop here. Thank you.
I made it clear, but that's what I understand.
Yeah. So Scott, you should unmute yourself.
Scott, you're muted.
Oh, I was just saying we should thank the speaker again. Sorry. Unless there was another question.
Yeah, I think I should have 2 questions, but I save my time. I think I only have 3 minutes for questions, right?
Basically, yeah. I guess we could have a quick question or something, but
yeah, let me ask you a quick question.
Let's do a quick question, sure.
So I'm thinking actually you're talking about the data that is not time series, okay? If you have time series data, think about this, they could have a high correlation between those columns. So probably you could, yeah, this is another question. I'm just seeing something, and also for the business, but probably there's even though we for the biomedical field, we do see a large portion of business, okay, in those longitudinal studies for time series data. So I'm just so I'm thinking probably you are talking about the data that is not time series or probably cross sectional, right?
Yes, this is a transaction data and it's not time.
Okay, thank you.
Thank you.
Great. Okay, let's thank the speaker again.